Welcome to Descriptive Statistics. Today we are diving into a fundamental concept, the independence of random variables. Understanding how different events interact or completely ignore each other is the bedrock of probability and modern data science. By the end of this lesson, you will know exactly what it means for variables to be independent, how to prove it mathematically, and why it is so crucial for solving real-world problems. Let us get started. Let us start by imagining you are flipping a coin in your bedroom, and at the exact same moment, a stranger is rolling a dice in another country. Does your coin flip magically influence their dice roll? Of course not. In statistics, when two variables have absolutely no effect on each other, we call them independent. Knowing the outcome of the first variable gives you zero clues, hints, or information about the outcome of the second. They simply mind their own business. This total absence of information transfer is the true practical meaning of statistical independence. Now that we understand the intuition, let us look at the mathematical rule that defines this behavior. In the language of probability, two random variables are independent if their joint behavior is just the simple combination of their individual behaviors. This gives us the fundamental multiplication rule. The formula states that the joint probability of x and y happening together is exactly equal to the marginal probability of x multiplied by the marginal probability of y. If this multiplication holds true for every single possible pair of values, the variables are truly independent. If even one pair fails, they are dependent. Before we see where this formula comes from, let us use it in a simple, everyday problem to build confidence. Suppose we flip a fair coin and roll a fair six-sided die at the same time. We want to prove mathematically that getting a head and rolling a 4 are independent events. First, we determine the marginal probability of getting a head. Since the coin is fair, the probability is 1 divided by 2. Next, we find the marginal probability of rolling a 4. A balanced die has 6 sides, so this probability is 1 out of 6. Continuing with our example, we now find the joint probability of both events happening together. The total number of possible combined outcomes is 12 because 2 coin outcomes multiplied by 6 die outcomes equals 12. Only one of these specific combinations is exactly a head and a 4, making the joint probability 1 out of 12. Finally, we apply our mathematical test. We multiply the marginal probability of the coin, 1/2, by the marginal probability of the die, 1/6. The result is 1/12, which perfectly matches our joint probability. The variables are indeed independent. Now that we have successfully used the multiplication rule, let us understand exactly where it comes from by looking at conditional probability. Conditional probability is the chance of an event happening given that another event has already happened. We start with the standard mathematical definition. The conditional probability of y given x equals the joint probability of x and y divided by the marginal probability of x. This equation connects joint and conditional probabilities. But remember our real-world intuition about independence? If variables x and y are truly independent, knowing the specific value of x provides absolutely no new information whatsoever about y. The condition essentially vanishes because it is useless. Continuing our derivation, we apply that exact logic. Because the variables are independent, the conditional probability of y given x just collapses back down to the marginal probability of y. It is the chance of y happening all by itself. We can substitute this marginal probability into the left side of our standard equation. By doing this, we are mathematically stating that the condition of x did not matter at all. To get the final, most famous formula for independence, we simply multiply both sides of this equation by the marginal probability of x. This perfectly isolates the joint probability, giving us our multiplication rule. So we have proven the multiplication rule. This brings us to a very common mistake in statistics: confusing the term uncorrelated with independent. Correlation measures only one specific type of relationship, which is a straight line linear relationship. If two variables are uncorrelated, it just means you cannot draw a straight line through their data points to predict one from the other. Independence, however, is a much stronger and stricter rule. It means there is absolutely no relationship whatsoever, not a straight line, not a curve, nothing. Therefore, independent variables are always uncorrelated, but uncorrelated variables might still be highly dependent. Let us see this difference with a concrete counterexample to prove that uncorrelated does not mean independent. Suppose we have a random variable x that can take three values, -1, 0, and +1, each with an equal probability of 1/3. Now let us define a second random variable y such that y equals x squared. We want to check if they are uncorrelated. First, we calculate the expected value or long-run average of x. By multiplying each possible value by its probability and adding them up, the negative and positive fractions cancel out perfectly, giving an expected value of 0. Moving forward with our calculation, we need to find the expected value of the product x times y to check for correlation. Since y is defined as x squared, the product x times y is actually x multiplied by x squared, which gives us x cubed. We calculate the expected value of x cubed using the exact same probability weights as before. Evaluating the cubes, -1 cubed is still -1 and 1 cubed is still 1. Just like before, the terms cancel each other out perfectly, resulting in an expected value of 0 for the product. We have established that the expected value of x times y is 0 and the product of their individual expected values is also 0. This means their covariance is 0, so they are completely uncorrelated. Now, let us test them for independence using our multiplication rule for the specific case where x is 0 and y is 0. The joint probability is 1/3. However, the marginal probability of x being 0 is 1/3 and the marginal probability of y being 0 is also 1/3. Multiplying 1/3 by 1/3 gives 1/9, which does not equal 1/3. They are highly dependent. Let us visualize what we just calculated. Looking at this graph, we have plotted the data points for our variables x and y. You can clearly see that the points form a perfect U-shaped curve, which visually proves that y is entirely dependent on x. However, the red line drawn through the center is the line of best fit. It is completely flat. A flat line indicates zero linear correlation. This visual perfectly captures why independence is a much stricter requirement than simply being uncorrelated. A strong non-linear relationship can easily hide behind a zero correlation score. This visual perfectly captures non-linear dependence. Now, let us explore another fascinating scenario called conditional independence. Sometimes, two variables appear to be strongly connected, but their connection is actually an illusion caused by a hidden third variable. For example, a child's shoe size and their reading vocabulary are highly dependent. Bigger shoes predict larger vocabularies, but big feet do not make you read better. The hidden variable is age. Older children have bigger feet and know more words. If we only look at children of the exact same age, the connection vanishes. Given age, shoe size and reading ability are conditionally independent. You might be wondering why we care so much about these hidden variables and independence in the real world. Dealing with multiple variables at the same time is incredibly complicated. Calculating joint probabilities directly requires massive amounts of data and complex math. However, if you can prove or assume that variables are independent, the math becomes beautifully simple through basic multiplication. This property is the entire foundation of many machine learning algorithms, like the naive Bayes classifier used to filter spam emails.
By assuming words appear independently, computers save enormous processing power while solving complex real world problems.
We have covered a lot of ground today. Let us review the key takeaways. First, independence means that knowing the outcome of one variable provides absolutely zero information about the other. Second, we prove this mathematically when the joint probability equals the product of the individual marginal probabilities. Third, always remember that while independent variables are uncorrelated variables can still be highly dependent in nonlinear ways. Finally, watch out for hidden variables that create illusions of dependence. You now have a solid foundation in statistical independence. Great job!